Hello, today's topic is application of angular momentum. First of all, we will take the conservation of angular momentum. Now, the rate of change of angular momentum is known as torque. A rate of change of angular momentum is known as torque. Means torque tau is dj upon dt in vector form. If tau is 0, then dj upon dt will be 0, or we can say dj upon dt equals to 0. It means dj, that's 0. dj means change in angular momentum. It means j final minus j initial, that will be 0. Or we can write j initial equals to j final. If torque on object or on a system is 0, then its angular momentum remains constant. If torque on an object or on a system is 0, then its angular momentum remains constant. Means it is conserved. Now, one example of conservation of angular momentum. This one is any pipe, hollow pipe. A rope is passed through this pipe with the rope, and a stone is tied to this rope, and this stone is drilled on a circular path. Its radius is capital R, this one. So this stone will move on this path. Suppose the angular speed in this path is omega 1. If we decrease the radius capital R, suppose it reaches up to this point, the radius becomes small r, it is small r, and is rotating. Suppose its angular velocity becomes omega 2, and we want to find the relation between omega 1 and omega 2. Either omega 2 will increase or it will decrease. Now we will find it. Now when the stone is revolving at the radius of capital R, then the initial angular momentum, that's Ji, will be I1 and omega 1. Here I1 is moment of inertia of the stone when it is moving at a distance capital R. I1 is m and r square. So we can also write Ji will be m r square into omega 1, number 1. Now when the radius is decreased, it becomes small r, then final angular momentum Jf, that will be I2 and omega 2. Here I2 will be m and small r square is capital R. So by the law of conservation of angular momentum, we can also write Ji and Jf must be equal. From 1 and 2, we can equate Ji and Jf from 1 and 2. Ji will be Jf. So m r square into omega 1, that will be m small r square into omega 2. This one is cancelled. We can easily find omega 2 will be capital R upon small r, whole square into omega 1. We know very well that capital R is greater than small r. So omega 2 will be greater than omega 1. If we decrease the radius of rotation, then the speed of the stone will increase. Same we can take another example, a stage, rotating stage, an object, and a person is standing on a stage which is rotating with angular speed omega 1. Same thing, this is the rotating, an object is or a person is standing here. These are the arms. Here is a object is rotating to the speed omega 1. Then at this time, this radius is r, so its I1 will be 2 into m and r square, and is rotating with angular speed omega 1. Now, if he fold his arms in this way, that the speed stage and object up to here. Now this distance will be smaller, so the speed of the person will change. Let's suppose omega 2, and this time I2 will be 2 times m and r square. Same thing, j1 and j2 must be same, ji and jr must be conserved. So the angular speed omega 2 will be greater than, here is omega 2 will be greater than omega 1. Means omega 2 will be greater than omega 1. These are the two examples of conservation of angular momentum. Now we want to compare the linear motion and the angular motion. Comparison of linear motion and angular motion. Here is linear motion and is angular motion. Now the first quantity is the role of mass in linear motion. Inertia. Same role is in angular motion is moment of inertia. Here is mass denoted by m. Here will be also known as inertia. Here moment of inertia denoted by I, that's mr square. Number 2, here is linear velocity or linear speed, that's v. Here is linear angular velocity denoted by omega. Number 3 is and linear acceleration. Here is angular acceleration, that's alpha denoted by a. Its unit is meter per second. It is a radian per second. It is meter per second square. It is a radian per second square. Linear displacement, that's s or x, y, z and so on. Y, z or r. It is angular displacement denoted by theta. Unit is radian. Now we can also write the equations of motion. First equation of motion is motion. V is u plus at. Here will be omega is omega naught plus alpha and t. Here omega naught is initial angular velocity, omega is final angular velocity. Now number 6, second equation of motion s is ut plus half at square. Here will be theta will be omega naught t plus half alpha and p square. Third equation of motion, that's v square is u square plus 2as. Here omega square will be omega naught square plus 2 times alpha and theta. We will use these equations of motion same as in linear motion. Now the number 8, force F. In the linear motion, its unit is SI unit is Newton. And here is same work is of torque. That's toe. Its SI unit is Newton into second. Newton into meter, not second. That's 9. We know the relation F is equals to ma. Here toe will be I and alpha at the place of linear acceleration. Here will be angular acceleration. At the place of m, here will be I, moment of inertia. Here is m is simply inertia. We can also write in vector form this way. Toe is I alpha. Now because P is mv, here is P is linear momentum. Here will be angular momentum J will be I and omega. We want to find in vector notation, then it will be J is I omega. J is angular momentum. Number 11. Kinetic energy is half mv square. Here rotational energy will be kinetic energy. Rotational half I and omega square. We know that power P is F dot V. We can also write here P rotational, that will be O dot omega. These are the comparisons of linear motion and angular motion. Relation between J and omega. We know that J is equals to R cross P. Here P is m v, but v is omega r. Here omega is angular velocity and r is radius of the path on which the object is rotating. So we can also write it J is equals to r p sine of theta and cap. If theta is 90 degree, then the maximum value of J will be R P, or we can also write here J will be R into MV on putting the value of V here. So J will be M R and omega R. Or we can also write J will be omega and M R square. Suppose an object is rotating about any axis, then it is made up of particles. The masses of the particles of the object which is rotating are m1, m2 and so on. That's mn. Distances of these particles from the axis of rotation are distances of these particles from axis of rotation are r1, r2 and rn. Then we can easily find the angular momentum of the particle having mass m1. angular momentum of m1, that's j1 will be m1 r1 square, and omega in rotational motion will be same for each particle. For m2 it will be j2, that will be m2, m different, r different, and but omega is same. In this way we can find the angular momentum of each particle separately. For nth particle, for mn, jn will be mn rn square and omega. Now we want to find the angular momentum of the total body, because the direction of j1, j2, j3 will be same. It is given by right hand thumb rule. So for complete body, j will be j1 plus j2 plus 1, or we can also write j will be omega is common, m1 r1 square plus m2 r2 square, and so on. That's j will be omega and sigma mr square. Here sigma mr square is I. Here sigma mr square is I, moment of inertia. So j will be I and omega. In the final relation between angular momentum, moment of inertia, and angular velocity. With the help of this one, we can easily define the I. We want to find the definition of this I, moment of inertia. Definition of moment of inertia. Because of j is I omega, if omega is 1 radian per second, then j will be I, or I will be j. We have to define moment of inertia. It means if an object is rotating about an axis with angular velocity 1 radian per second, then angular momentum of the object will be equal, only in magnitude, will be equal to moment of inertia of the object about that axis, to the moment of inertia about that axis. Now the relation between tau and I. We know that tau is r cross f, or tau will be r f sine of theta n cap. If theta is 90 degree, then the maximum value of tau will be r f. Because of f is ma, or we can also write here at the place of a is alpha and r, so f will be m, r and alpha. So we can write here tau will be r, m, r and alpha, or tau will be alpha and mr square. In rotational motion, an object is rotating about an axis, then alpha for each particle will be same. As angular velocity is same. So if we want to write the relation number 1 for complete body, we can also write for complete body tau will be alpha is same. It is different for different particles, so we can also write sigma mr square. Here sigma mr square is moment of inertia I, or we can also write tau will be I alpha. Again, we can define from here the definition of I, definition of moment of inertia. Because of 2 is I alpha, if alpha is 1 radian per second square, then 2 will be I, or I will be 2, same. We want to define I. So I will be 2. Means if an object is rotating with angular acceleration 1 radian per second square, then the torque on the object, that's magnitude only, will be equal to the moment of inertia of the object, the mi of the object, about that axis.